In the previous video, we got some basic idea of logical effort. So we shall continue in this video the same logical effort. So it was defined that the delay, which is uniqueness delay, is given by f plus p, where f was given by g into h, where g was defined as a logical effort, h is defined as the electrical effort, p is the parasitic delay. We actually define what is the value of g for different basic gates, that is NAND gate, NOR gate, and we also defined how to estimate the value of f. Now let us try to see what is the D of a particular inverter as well as a NAND gate. So we know that D is given by f plus p, where f is given by g into h plus p. This is the parasitic delay. G is the logical effort, h is the electrical effort. Now you can see on the x-axis the electrical effort is given in ratio, which is C out by C in. So if C out by C in is equal to 0, that is without having any load. So when there is no load, we know that this h is equal to 0. When h is equal to 0, it is only the p that is coming into picture. So meaning, so when there is no C out, that is when h is equal to 0, we have the normalized delay D is given by 1 for the inverter and it is 2 for the NAND gate. So we know that when G into H becoming 0, because H equal to 0, the delay is nothing but only P. So P is nothing but the parasitic delay. Parasitic delay in case of the value of P for an inverter is 1, whereas the value of P for a 2 input NAND gate is 2. So that's why it is when H value is equal to 0, so the delay is 1 for the inverter and it is 2 for the NAND gate, 2 input NAND gate. So now you can see, so as the value of the electrical effort increases, meaning as the value of C out increases. Now this is how the value of the overall delay of the inverter looks like, and this is how the overall delay of the 2 input NAND gate looks like. So we know that this line is given by this is P here, this is P plus G into H. So we know what is the value of G for a 2 input NAND gate. It is 4 by 3. So if we can remember, G is given by C in of the gate given by C in of the inverter. So since it's a 2 input NAND gate, we have the input capacitance of the NAND gate is given by 4, and of the inverter it is 3. That's why it is 4 by 3 here, and P is equal to 2. That is the parasitic delay of the 2 input NAND gate is 2. So D happens to be this is G into H plus 2. So this is G into H plus P here. So this H varies as per the value of your this on x-axis. So that's why as the value of H changes, so this is increasing. So now you can see, so this is the parasitic delay and this is the effort delay F. Now for an inverter, G is equal to 1, P is equal to 1. So that's why we can write D, the overall delay is given by G into H plus P. So G is nothing but 1, that's why it is H plus P. So as the value of H increases, the overall D is increasing. So it is H plus P. So P is equal to 1 for inverter, whereas P is equal to 2 for a 2 input NAND gate. So we have seen this, how do we estimate the value of G for an inverter, G for a 2 input NAND gate, this is 2 input NOR gate. Now the summary of logical effort for common gates. So for a NAND gate it is, for a 2 input NAND gate is 4 by 3, for a 3 input NAND gate is 5 by 3. So why you can see in the denominator is always 3, for neither it is whether it is a NOR gate or NAND gate, it is 3 because the C in of the inverter happens to be always 3, which is given here. Now this is what is 2 plus 1 3, here it is 2 plus 2 it is 4, here it is 4 plus 1 5. So this way we can estimate the value of G of different gates, so depending on the number of gates. And in general we can write the G, the logical effort of a NAND gate, n input NAND gate, as n plus 2 divided by 3. Now for a NOR gate it is 2n plus 1 by 3. Now we also found in the previous video how do we estimate the value of parasitic delay P. So for an inverter it is 1, so which is given by the parasitic, that is at the output divided by the parasitic of the inverter. For the inverter it is 3 by 3. For the NAND gate it is we actually found, okay, how do we estimate the value of P for a NAND gate. So if you just recollect, okay, how did we find the P of a so this is how did we find the P of a NAND gate. So the intrinsic capacitance at the output node is, here it is 2, 2, 2, which is 6, and to that of the inverter it is 3, it is 6 by 3, which happens to be 2 here. So that's what is written here. So that's why for a 2 input NAND gate the value of P is 2. If the value of if the number of inputs are 3, now it is 3, that is this will become 3. So how it becomes 3 is, now here we're going to have, this is 2 plus 2 plus another 2, now this will become, so now it is when you're stacking 3 here, now it will become 3, now it will become, so 3 plus 3 plus 3, now it is 3 plus 6, which happens to be 9, so 9 by 3 happens to be 3 here. So that's how we can estimate the value of P here. So this is the different values of P for different gate depending on the number of inputs. We can certainly estimate what is the oscillating frequency of this particular N stage ring oscillator. Now we know it's all made out of inverters. The logical effort of an inverter, which is given by C in of the inverter divided by C in of the inverter. G happens to be 1. So we can also find out what is the value of H here. Now H is also 1 because H is nothing but C out by C in. So because on the input and output side you have the same capacitance, H is equal to 1. Parasitic delay for an inverter is also 1. So the stage delay, which is nothing but G into H plus P, which happens to be 2 now. We can actually estimate the overall time here. Now since you have n stages, so it is given by n into d. So this is the total time. The frequency is given by, so this particular expression. So we have, this is the frequency of the oscillation, which is given by 1 over 2 into n into d. So this n into d happens to be the overall time. So divided by 2 happens to be half of the time. The oscillating frequency will be 1/4 of okay, this is 1 by 4 n. So this is 1 by 4 n is the oscillating frequency of this ring oscillator. So we can actually estimate what is the delay of this fan out 4 inverter. We know that the value of G here is 1, whereas when it comes to H, it is at the output we have 4 inverters. Now it is 4 here, it is 1, this H becomes 4. The P is 1 here, so then the D becomes G into H, which happens to be 1 into 4, which is 4 plus 1, which is 5. So let us have a look at what is the value. Now you can see it is G is equal to 1, H is equal to 4, and parasitic delay of the inverter is 1, and the stage delay is, overall stage delay is P into H plus, or G into H plus P. So that's what is 5 given here. So likewise we can estimate the delay of a multi-stage logic network. Now since we have a number of gates connected here, now it's not only a single gate. Now when it is a multi-stage logical network, we go for the path effort, that is path logical effort, path electrical effort, and path effort. Now we can actually estimate the logical effort of the path, which is given by capital G, which is a product of the different G's of the gates which are coming in that path, and path electrical effort, this is for the entire path, it is given by C out by C in. So C out of the path divided by C in of the path. So overall path effort F is given by, F is a product of different F's of the individual stage. So where F we know that G into H. So we can write F as a product of Fi's, and where each Fi is a product of G into H. So we shall have a look at a particular case where we have an inverter driving a NOR gate is connected to an AND gate, and it's connected to another inverter which is connected to finally a 20-unit load capacitance. We shall take this example and try to find out how do we estimate the. So this is what we are looking at. It's the same example. Now we are supposed to find out what is the overall delay of this path. Now we know that this is the inverter of size 10 here. Now since we know that inverter of unit size is going to have a capacitance of 1 unit, since it is 10 here, so we're going to have an input capacitance of 10 units here. Since the output capacitance is 20 units, so overall H, the electrical effort of this entire path is given by 20 divided by 10. So C out is 20, the C in is 10 here, so that's why it is 20 by 10, which is equal to 2. And we know that the path logical effort is given by the product of individual logical effort of the different gates. So it is G1, G2, G3, G4. G1 is the logical effort of this inverter. G2 is the logical effort of this 2-input NOR gate. G3 is for the 2-input AND gate. G4 is for the inverter. We know that for the 2-input for the inverter, the logical effort is 1. So that's why we written wherever G1 is there, it is 1. For G4, it's again 1 here. This is the logical effort. Whereas for the 2-input NOR gate, the logical effort is 5 by 3. For the NAND gate, it is 4 by 3. So overall G is the path logical effort given by 20 divided by 9. So it's the product of all G's. Similarly, we can estimate the path parasitic delay, which is P is given by P1 plus P2 plus, because all the delays we're going to add on. So this is now P1 plus P2 plus P3 up to P4. Now we know that for the inverters it is 1, 1, whereas for the NAND and NOR gates it is N. So since it's a 2-input NAND and NOR gate, it is 1 plus 2 plus 2 plus 1, which happens to be 6 now. So we know what is the overall logical effort and the parasitic delay. So we know that the overall delay, capital D, is given by, so this is the delay of the path, which is given by the path effort of that path plus this is the parasitic effect of that path. So we know that this capital F is again given by G into H. So this is the value of G, which is 20 by 9, and this is the value of H. So P, we know that this is so-and-so. So overall delay of the network is now 10.44 units. So once we know 10.44 as the overall delay, then we are supposed to size the transistor in such a way that so that it gives a minimum delay of 10.44. In order to have a delay of 10.44, what should be the dimensions of each of the transistors that are used to get these NAND gate and NOR gate as well as the inverters. Now for the first inverter, the dimension, the scaling factor is given. For others, it is X, Y, Z. So we are supposed to estimate the values of X, Y, Z so that it can give a delay of 10.44, which is an optimized delay. Now we know that in the previous classes, so suppose if F is the overall fan out, so this F is given by F to the power N, where N happens to be the number of stages here. So since N is equal to 4, here it is 1, 2, 3, 4 now. So these are 4 stages you have, and from which you can get the value of small f, which happens to be 1.451. And we know that f is given by G into H. So we know what is F4. So all f's will be having the same value of 1.451. So F4 is equal to G4 into H4. So we know G4 is for an inverter, it is 1. F4 is 1.45. So H4. So as we know that H4 is nothing but the electrical effort of this, which is given by the output capacitance to the input capacitance. We know the output capacitance, we don't know the input capacitance because we don't know the sizing of this inverter, which is 4 here. Now we can actually find out what is the size of the inverter here. So using this, so whatever the value of Z comes here, so you can estimate the value of Z by substituting this onto this equation. Now we know the value of G4, we know the value of F4, so that H4 can be substituted, can be obtained using this equation. So H4 is actually 20 by Z. So out of H4 20 by Z, we don't know the